Algebra 1, 3.1, Solving Systems Graphically. We're going to start by reading and highlighting. Let's go to work. Let's get my trusty little highlighter out here. Let's go with a blue today. All right, solving systems graphically. Before I really get into the reading and highlighting, I want to remind you that systems of equations are when you solve two or more equations, or those could be inequalities. Remember, equations and inequalities are basically the same thing, just with a different sign. So we're solving two or more equations or inequalities simultaneously. What does a simultaneously mean? At the same time. So please write that at the top of your page as we begin. Maybe you can be a little bit neater than I and get it up in there. Okay, let's read and highlight. Now that we know how to solve complicated equations, we move on to solving what are called systems of equations. Systems of equations is when you solve multiple equations with multiple variables and are looking for the values of the variables to represent the equations that are true at the same time. I'm going to clean that up. Systems equations, when you solve multiple equations and multiple variables, and all of the equations are true at the same time. Okay, that looks important to me. We will mainly be dealing with two variables and two equations. That's cool. We'll keep it simple for us at the beginning. But can solve most systems equations as long as you use the same number of equations as variables. As a quick example, consider the following system. X plus y equals 5 and x minus y equals 1. It doesn't take too much work to verify the solution of this system is x equals 3 and y equals 2. Notice that those x values or values for x and y make both equations true at the same time. 3 plus 2 equals 5, and 3 minus 2 equals 1. Okay, so all they did was plug those values in. The question remains, though, how do you get that solution? Well, the first method we're going to talk about is solving with graphs. If we have our equations set up by using the x and y variables, we can graph both equations. We've been doing that for months. Let's see how this helps us. To start, let's graph the first equation, x plus y equals 5. Remember, you can do this a couple of ways. We can simply make an xy chart and plot the points. Or, alternately, we could get the equation in slope-intercept form. That's my favorite. And then graph. As a reminder to you, what is slope-intercept form? That's y equals mx plus b. And I think they're going to do that down here below. So let's start with the xy chart. Remember that xy chart can pick x values and substitute those in to find the y values. This one happens to be a lazy t-chart, okay, right here. They chose the x values, plugged those in, and solved to get these y values, and then you could plot them. Now you can plot those points on a coordinate plane and connect to get your graph. If you don't like the xy chart method, we could turn the equation into slope-intercept form. That's my favorite. Look what happens here. We start by getting that y alone. So they subtract x from both sides and cancels on the left and ends up being 5 plus a negative x, but we would like to rewrite that because we like it to be in this form, y equals mx plus b. Now I can see that my y-intercept is 5 and my slope is negative 1. Either way, we get the graph that looks like this. Remember, it was y equals negative x plus 5. And we start with our y-intercept is 5, and our slope is negative 1. So down 1 over 1, down 1 over 1, down 1 over 1. And we get that line. Now, we can graph the second equation, x minus y equals 1, the same way. It turns into y equals x minus 1 and gives us this following graph, this one right here. The other one was already done for us, right? Let's check that. Just for fun, my y-intercept is negative 1. There's negative 1. And my slope is 1. So up 1 over 1, up 1 over 1, up 1 over 1. I can see that's all true. What do you notice about the two lines? Well, you should notice that they intersect. At what point do they intersect? Well, the intersection is 3, 2. And you can see that simply right there. 3, 2. That is the point, 3, 2. Which means that x equals 3 and y equals 2. What does that tell us about solving systems of equation using graph? Well, it tells us the point of intersection is the solution to the system, because that point is the only point on both lines. Assuming you're dealing only with linear equations for now, later we'll have other ones. In fact, we sometimes write a solution to a system of equations as a point. We sometimes write the solution to a system of equation as a point. So the solution to this system is 3, 2. Let's try another example. What would be the solution to the system of equations listed below? We'll leave it as an exercise to verify the following equations with the same system written in slope-intercept form. Let's do that just super quick for fun. Here I would subtract 4x from both sides, right? So I'd have 2y equals negative 4x plus 6. Divide by 2, divide by 2. So y equals negative 2x plus 3. Beautiful. Second one, I would add x to both sides. So I'd end up with 2y equals x minus 4. Divide by 2. So y equals 1/2 x minus, 2. 4 divided by 2 is 2. And look, there it is as well. So now let's graph those two equations. Quickly they were y equals negative 2x plus 3 and y equals 1/2 x minus 2. Just double checking. Yep, those are my two equations. Starting with my first one, my y-intercept is 3. My slope is negative 2, so down 2 over 1. Perfect. My second equation, which I'll say right here, is my y-intercept is negative 2. My slope is 1/2, so up 1 over 2. And that's correct as well. Now, it looks as though like the graphs intersect at the point 2, negative 1. And we can verify that by substituting into the original equation as follows. And look, we put the 2 in for the x. 2 goes in for the x. And the 1 goes in for the y. And look, it works. Same way on the second equation. That means we have a correct solution. Estimating using a graph. So far, solutions have been integer values. Remember, integers are positive and negative whole numbers and 0. Okay, so we've had nice, easy round numbers. But it won't always be the case. We can still use a graphing method to get a decent estimate, even if it's not a nice solution. For example, let's look at these two equations, and they are graphed as such. However, we can see that that point of intersection is not exactly a lattice point. It's a little bit bigger than 1, and it's almost 2.5 there. Okay, so it's not always going to be a beautiful lattice point. Some people would say that's what makes the graphing method the least accurate method for solving systems of equations. And while that's true, with today's technology, we can find that exact point given the graph using technology. But if we were doing it by hand, it would be much less accurate. Note that the x-coordinate where the lines intersect is a little more than 1. And the y-coordinate at the intersection is a little more than 2. So we might estimate the solution to be 1 1/4 and 2 1/3, or the decimal equivalent. The actual solution is 1.2 and 2.4 for the system. We can discover later how to find that exact system or solution using technology. So, what have we talked about here? Solving systems of equations. There will be 3 methods for solving systems. The first one that we talked about today is graphing. And that's simply where you graph both equations and look for the intersection. Now, I want to tell you that there's not always going to be an intersection. I could have a couple different possibilities here. It's got 3 coordinate planes here. I could have, these 3 lines, and here's what it could be with it. In this first one, I could have 2 lines that intersect like this, and this has 1 solution. I could also have 2 lines that are parallel, and therefore they would never intersect. That would have no solution. And finally, I could have 2 lines that are essentially the same line, lying right on top of each other. And that would be infinitely many solutions. So that could happen when dealing with a system. The one that we're going to deal with the most is when it has 1 solution. Okay? Something cool I'm going to give you right now about these 2. It's interesting when they're parallel or essentially the same line, they have the same slope. We'll come back and talk about that more in the future. So that's section 3.1, your reading and highlighting. I hope that was beneficial for you. I hope it made sense. And that's your introduction to solving systems of equations by graphing. Have a great day.